Hello, my name is Jaden Finney, and this is Physics Lab 4 titled Circuits. Alright, so the purpose of this lab is to familiarize ourselves with simple series and RC circuits to explore voltage across the circuit. Sorry. RC circuits stand for resistor capacitor circuits. There's always power in a circuit, that's why it's just RC. Current and potential difference will be examined and compared across many different values. This experiment was conducted virtually through FetLab. All right, so we have four main models for this experiment. So first we have the node rule, which basically means the current going in a circuit must equal the current going out. And then we also have the loop rule, which is potential difference equals 0 after the loop of a circuit. Resistance is defined as R equals the voltage divided by the current. You also rearrange this by saying voltage equals current times resistance, etc., etc. And capacitance is the opposite of resistance. So when you're trying to calculate resistance, capacitance is going to be the inverse of that when you're doing summations. All right, so in this experiment, through FetLab, we first constructed a simple series circuit with two batteries, a couple resistors, and we had some voltmeters and ammeters to read the current and voltage. At the bottom right, you can see the circuit I constructed in FetLab. The predicted current I got was 0.0203 amps. This I computed through the loop rule. The actual current for the experiment was 0.02 amps, and the reverse current was actually negative of that, going in the negative direction. So the calculation, I calculated the potential difference around the circuit from multiple points. I did from B to A, C to A, C to D to C, F to E, and as you notice, as you get different values, the theorem is that the sum of these potentials must equal 0, and this is actually found true when we actually add these values up. And the ammeter does not change because the current is not disrupted in the circuit. So the ammeter, I replaced the voltmeter with the ammeter, and I made it parallel to the 100 ohm resistor. And after doing that, the current increased to 0.06 amps from 0.02, and it splits into the channel with the ammeter. And now we did a connection to RC circuit as well. So we had a 10 ohm resistor, a 200 MF capacitor in series, and then so we had some observations. So first the light bulb shines, and then current flowed into the capacitor, which charged, and once the capacitor was fully charged, and then the current would decrease until the capacitor fully discharged, and the light bulb would begin to dim, and then it powered off, and then there'd be no current flowing through the system. The results for the 10 ohm setup, there was a charge time of 14.3 seconds and discharge time of 15.2 seconds. And then as we increased the resistance to 20 ohms, the charging time increased and the discharging time decreased as well by about 10 to 11 seconds per parameter. So as a result, so right now we have the ln of v as v naught versus time. And to find the slope, RC is considered the time constant. So the time constant is equal to -1 divided by the slope, which we found to be -0.01583. So the RC constant was about 6.3 seconds. And as you can see, it's a pretty straight line, negatively downward sloping graph. So what if I was in the lab in real life and used an actual ammeter? The ammeter would have its own resistance, causing greater resistance altogether. And what if I use a real battery to charge a real capacitor? Then there would be actually resistance in the wires of the capacitor, which technically would also cause a greater resistance overall, and the battery would charge almost instantaneously. So in short, we examined how simple types of circuits operate, both in series and parallel components. We analyze how delta potential or potential difference changes across different parameters and how different electrical components work. To set up a more ideal experiment, avoiding rounding errors, reaction time for handling the stopwatch would help. Thank you for watching my video.